So in my previous video, I explained about the torque equation of three-phase induction motor under standstill condition. So under standstill condition, we are calling the torque as starting torque. Okay. So how we are getting the starting torque under the standstill condition of a rotor, and what is the condition of starting torque, and what is the equation of maximum starting torque. Okay, so I already explained about the equation of torque equation of three-phase induction motor under standstill condition, and in this video now I am going to explain about how we are going to get the torque equation of three-phase induction motor under running condition of a rotor. Clear? So you can remember the most important point: under running condition of rotor. Under running condition of rotor means, the speed of the rotor, or the rotor is rotating at definitely some speed. Okay, for example, n represents the speed of the rotor. It means that under running condition of a rotor means capital N is not equal to 0. Okay, not equal to 0 means, for example, I am assuming the value of n is equal to, 900 rpm. Okay, so under running condition of a rotor means definitely rotor is rotating at some speed. For example, in this case, I am assuming that 900 rpm is the speed of the rotor. Clear? And you know that synchronous speed of rotating magnetic field, that is n suffix s. So n suffix s is the synchronous speed of a rotating magnetic field, and you know that synchronous speed of rotating magnetic field is always not equal to 0, and the value of this synchronous speed is always depending upon the supplied frequency as well as the number of poles on the stator. So that is the reason why the formula we are using to calculate the synchronous speed of induction motor is 120F divided by P. Okay, so this is the formula we are using to calculate the synchronous speed of a induction motor. Clear? So now coming to the point. So rotor is under rotating condition means, so the synchronous speed value, for example, I am assuming the speed of the synchronous speed ns is equal to, for example, I am assuming 1500 rpm is the, so 1500 rpm is the synchronous speed of the value, and here n is the rotor rotating at 900 rpm. Now you can directly use these two values for getting the value of slip. So S is equal to ns minus n divided by ns. So it means that ns value we assumed that 1500, and the value of n we assumed is 900 divided by 1500. Okay, so what is the remaining? So 600 divided by 1500. So by two zeros and two zeros we are cancelling, so 6 divided by 15. So by calculating this, you are not going to get 1 as well as you are not going to get 0. It means that the value, by calculating this value, you are going to get the value of this slip between the range 0 to 1 only. It means that by calculating this 6 divided by 15, so you are getting the value of slip as 0.4. Okay, so you can remember one most important point: under running condition of a rotor, the slip is definitely, you will get the value of slip definitely between the range of 0 and 1 only. But in case of standstill condition of a rotor, slip is always 1. Okay, so that is the reason why in case of running condition of a rotor, slip is always, you will get between the range of what? 0 to 1 only. Okay, you are not going to get the value of slip 1, and also you are not going to get the value of 0. Always between the 0 and 1 only. Okay, so that is the reason why we already discussed about the concept of rotor frequency. Okay, so in standstill condition of a rotor, in standstill condition of a rotor, so rotor frequency here F suffix R represents the rotor frequency. Okay, so under standstill condition of a rotor frequency is always is equal to supplied frequency. But in case of running condition of a rotor frequency is equal to S times the supplied frequency. Okay, so that is the reason why in case of running condition of a rotor, definitely you will get the value of slip between the 0 to 1 only. It means that we are going to including the value of S is equal to some value, that is, for example, in this case you are getting 0.4. So that is the reason why under running condition of the rotor, you need to multiply the term S, that the slip term S, to all the frequency components. Okay, so under running condition of the rotor, we are going to consider, so we need to consider this slip for all the frequency components. Okay, so what are the frequency components which are available in the equivalent circuit diagram of a induction motor? So first thing is EMF generated in the rotor, E2. E2 is the frequency component. So that is the reason why in case of running condition of a rotor, instead of E2, we need to consider S into E2. Okay, because E2 is the frequency component. Now X2 is also a frequency component. How we can identify whether the X2 is frequency component or not means by using the formula X is equal to omega L. So omega means 2 pi F and L is always L. Here you know that under running condition of a rotor frequency is equal to S times the supplied frequency. So that you can directly write X2 is equal to 2 pi into F. Instead of F, I need to place S into F and L as it is. So that X2 is equal to S into 2 pi F L. Okay, so that is the reason why instead of, in case of running condition of a rotor, you need to consider S into X2. Okay, S into X2. Here X2 is the frequency component. So that in case of analysis of a induction motor under the running condition of rotor, you need to multiply slip to X2 as well as you need to multiply slip to E2, because E2 is the frequency component term and also X2 is the frequency component term. Now what about the R2? R2 is not a frequency component term. So that is the reason why we are not going to multiply S to the R2, and even we are not going to multiplying S to I2 also, because I2 is also not a frequency component. Okay, only the frequency component terms are E2 and X2. It means that under running condition of a rotor, we need to multiply S to E2 as well as S to X2. Clear? So in my previous video, I explained about the how to write the expression of rotor current, how to write the expression of power factor of rotor, and also I explained about the expression of torque. Okay, so now with the help of all these concepts, I am going to derive the derivation of a torque under the running condition. Clear? Now you can observe here. First I will draw the equivalent circuit diagram of a three-phase induction motor, and after that I am going to write the expressions for E2, cos pi 2 and also I2. Okay, after that I am going to get the torque equation under the running condition as well as the torque equation under the running condition with maximum condition. Okay, maximum torque condition. Clear? So here, so three phase induction motor means, to analyze the three phase induction motor, you consider single phase equivalent circuit. That is enough. And you know that three phase induction motor is also called as a rotating transformer. Okay, so that is the reason why the equivalent circuit diagram of induction motor is always similar to the transformer. So that is the reason why I am going to consider the equivalent circuit diagram. Now you can observe here, with the help of this equivalent circuit, you can easily understand how we are going to write the expression of rotor current and how we are going to get the impedance. Okay, now for example, so this is the primary side and this one is the secondary side. It means that, so this circuit represents the stator and this circuit represents the rotor. So here R1 X1 and combination of these it will give Z1, and here R2 and this one is X2. It's a combination of these two gives Z2. And you know that, so as per the principle of operation of induction motor, EMF E1 is generated in the stator as well as in the rotor. So whenever there is a generation of, or whenever there is a production of EMF E2 in the rotor, because of this there is a flow of current I2 in the rotor circuit. So that is the reason why I2 we are calling as rotor current. Okay, and this one is the load. Clear? Now here first I am going to talk about the EMF generated in the rotor. So that is the reason why, so first thing is EMF generated. So EMF generated in rotor. Okay, what is that EMF generated in rotor? E2. And you know that we are talking about running condition. So that what? Under running condition, E2 is the frequency component. So that is the reason why instead of E2 we need to consider S into E2. Okay, so this is first point. Now coming to the second one, that is rotor current. Okay, rotor current. So you can observe one thing, I consider only single phase equivalent circuit. It means that what? Whatever the values we are considering, all are per phase values only. Okay, so rotor current I2. So rotor current I2, what is the expression of I2 from the rotor circuit? Because of I2 only current is flowing, and this circuit consisting of R2 and X2 parameters. So that what? I2 is equal to E2 divided by Z2. So that is the reason why I2 is equal to E2 divided by Z2. Clear? Now I2 is equal to E2. E2 means instead of E2 I need to consider S into E2 divided by Z2. Z2 means what? So Z2 means under root R2 square, and here X2 square means I need to consider S into X2 square. Okay, so this is the expression of rotor current under running condition. And third one is what? Power factor of rotor. So power factor of rotor means what? Cos pi 2. Okay, so cos pi 2 is the power factor of rotor, and I already defined the definition of power factor of rotor. Okay, how to define the definition of power factor of the rotor? It is defined as a ratio of rotor resistance to the rotor impedance. It means what? R2 divided by Z2. So that R2 is not a frequency component, so that I am directly considering R2 divided by Z2 means what? As it is we are placing under root R2 square plus S into X2 square. In case of running condition, you always multiply S, that is slip, to all frequency components. Clear? So now you know that. So instead of E2 we need to substitute S into E2. Instead of I2 I need to directly consider this expression, and instead of cos pi 2 I need to consider this expression. Now coming to the expression of torque. Okay, so we already know that from the working principle of induction motor, you know that torque is directly proportional to E2 I2 cos pi 2. Clear? So your torque is directly proportional to E2 I2 cos pi 2. Now here what I am doing, just I am neglecting this proportional. So that is the reason why by neglecting this proportional you will get proportional constant K. Okay, now as it is remaining terms, I2 E2 I2 cos pi 2. Okay, just now we discussed about E2 I2 and cos pi 2. Just see here, these three are the equations we need to substitute instead of these three terms. Clear? So K is a constant term, just forget about this. After that, at the end of the video I will substitute the value of constant K value here. Okay, so just see here, so T is equal to K into, what is E2 actually? E2 is what? S into E2. Next to, what is I2? I2 means what? I2 is E2 divided by Z2, and you know that I2 is equal to E2 divided by Z2 means this is also S into E2. And what is cos pi 2? Cos pi 2 is R2 divided by Z2. Okay, now T is equal to K into, so S into E2, S into E2, and the value of S into E2 divided by Z2 is what? So S into E2 divided by the value of Z2 is given by under root R2 square plus S into X2 square. Now here also same, R2 divided by the value of Z2 is what? So under root R2 square plus, so here X2 into S square. Clear? Now simplify this expression. Now T is equal to K into S into S square, E2 into E2. So that one is E2 square, and the numerator consisting of another term, that is R2 divided by, so under root R2 square plus S into X2 square. Here also same, under root R2 square plus S into X2 square. It will give what? So it will give R2 square plus S into X2 square. Clear? So T is equal to K into S square into E2 square into R2 divided by under root R2 square plus S into X2 square. Now coming to the constant term K. Okay, so in case of three-phase induction motor, the value of K is always, we are considering 3 divided by 2 pi ns. Okay, so this is the value of constant K, and here remaining is what? S square E2 square into R2 divided by R2 square plus S into X2 square. Clear? So now we can directly consider, so this is the equation of a torque. Okay, equation of a torque. But when we are getting this torque equation, when the rotor is under running condition, so that is the reason why this equation number 1 is also called as running torque. Okay, so that is the reason why here I am writing like this. So running torque. Okay, so I am writing running torque. T running means running torque is equal to 3 divided by 2 pi ns into S square into E2 square into R2 divided by, so R2 square plus S into X2 square. Okay, so now equation number 2. So this equation number 2 represents the running torque of a three-phase induction motor. Clear? So I think you are clear. Now coming to the most important point, that is when this running torque is maximum. Okay, now just up to this equation number 2, we can directly say that under running condition of a rotor, so the expression of torque is equal to 3 divided by 2 pi ns into S square into E2 square into R2 divided by R2 square plus S into X2 square. But when this running torque is maximum, okay, now we need to get the condition required to get the maximum running torque. Okay, so to get that condition, what we need to do? We need to consider only the terms like this. Okay, just see here. So running torque is equal to, so you know that, so this term is always constant K, so that I am directly considering K, and here E2 square, here E2 is the EMF generated in the rotor. Okay, so you can directly say that what? So E2 is constant. Okay, E2 is constant, so that we can directly neglect this term. And what is the remaining thing? S is not constant, because what? S is depending upon the rotation of the rotor. It means that from starting condition to the from starting to the ending, the value of S is changed. So that is the reason why S is not a constant, so that we need to consider S here. Okay, and here R2 is also not a constant value, because in case of slip ring induction motor, the value of R2 is not fixed, because by using the slip ring concept, we can directly add the external resistance. Okay, so that is the reason why E2 square, that is E2 we are neglecting, because E2 is a constant sum. Okay, so that is the reason why T running or running torque is equal to K into S into R2 divided by, so here R2 square plus S into X2 square. Okay, now assume this is equation number 3. Okay, Now to get the maximum condition required to get the maximum running torque. Okay, so for that what we need to do, we need to differentiate equation number 3 with respect to slip S and make it is equal to 0. Okay, so differentiate equation number 3 and make it is equal to, so differentiate equation number 3 with respect to S and make it is equal to 0. Okay, so that is the reason why here I am writing here. So D running torque, okay, D running torque divided by ds is equal to, so D divided by ds of k into s into r2 divided by, so r2 square plus s into x2 square, make it is equal to 0. Clear? Now see here, k is constant term, so I'm bringing this k to outside and remaining is what? So D divided by ds of s into r2 divided by, so r2 square plus s into x2 square, and make it is equal to 0. You can observe here d by ds of numerator consisting of one value and denominator consisting of one value, so that I can directly consider the formula to solve this, that is u divided by v. Okay, u by v formula I am using. So what is the formula of u by v? So u dash v minus u v dash divided by v square. Okay, so this is the formula I am using to solve this. Okay, now see here, u is the value of u is equal to s into r2 and value of v is equal to r2 square plus s into x2 square. Okay, now apply this formula to get the final result. Okay, now you can use here, this is most important concept. If you know this concept clearly, then you can easily analyze and you can easily solve the problems based on the induction machine. Clear? Now see here, what is the expression? So d running divided by ds is equal to k into d by ds of s into r2 divided by, so r2 square plus s into x2 whole square. Now apply u by v formula. Okay, now so and make it is equal to 0. So this numerator is u, denominator is v, so that by applying that formula, so d by ds of, so u dash means with respect to s, u dash is small, definitely you will get r2. Okay, so d by ds of u dash means you are getting with respect to s, so that you are getting what? R2, because ds by ds gives 1 and the remaining term is r2. Okay, so r2 into, what is the value of v, that is what? Directly I am writing instead of v, u dash v. Okay, u dash v means u dash value is r2 and v is always as it is I am placing here, that is s into x2 square minus u v dash. Okay, just observe here. Okay, u dash v minus u v dash. U dash means you are getting r2 because with respect to s, so that s is neglecting, so r2 is a term of u dash and v is always the denominator, so that directly I am placing r2 square plus s into x2 square minus, again the formula is what? U means what? U is s into r2, I am directly substituting, and v dash means here, v dash means we are differentiating with respect to s, so that v dash means what? You will get 2 into s into x2. Okay, so just see here, so d by ds of v dash means what? With respect to s means, so this term is what? S square into x2 square, so that with respect to s, so that it will give what? So s square means 2s into x2 square, as it is we are placing like this. Okay, just 2s into x2 square, so divided by v square, that is what? R2 square s into x2 square whole square and make it is equal to 0. Clear? Now simplify here. So here I'm directly writing here. So r2 into r2 square means what? r2 power 3 plus r2 into s into x2 square. It will gives a value of what? So it will gives a value of s square r2 and x2 square. Okay, next coming to second, this value. So s into s square 2 and r2, it means what? So 2 times of s square r2 x2 square divided by r2 square plus s into x2 square whole square, make it is equal to 0. Okay, now you can observe here. So here k into this complete value which is equal to 0, so that we can directly make it is equal to 0 means, so denominator part it's going to multiply 0 means you will get only what? So k into, okay, this k is also, if for example if you are bringing this k to right side, so 0 divided by something means you will get 0 only, so that this k is also gone. Now what is the remaining term? So denominator r2 square plus s into x2 square whole square is multiplied with 0, you will get 0, and here k is there. If I am going to bringing this k to right side, so 0 divided by k means 0. So remaining term is what? Remaining term is r2 power 3 plus s square r2 into x2 square minus 2 into s square r2 into x2 square is equal to 0. Okay, now you can observe here. So s square r2 x2 square minus 2 times of s square r2 x square, it means what? This is 2 times, this is 1 time, so we can directly subtract, then you will get what? r2 power 3 minus s square into r2 into x2 square is equal to 0. Okay, now take common here r2 from both the terms, then you will get what? You will get, take common r2, then you will get what? So r2 square minus s into x2 square is equal to 0. Okay, now from this expression we can directly write what? We can directly write, so I'm writing here. So from this expression I can directly write, so r2 take common, it means, so r2 square minus s into x2 square is equal to 0. So from this I can directly write r2 square minus s into x2 square is equal to 0. So from this, sorry, this is also s square only, na? Just you can observe here. Okay, so this is what we are taking common only r2, so this is s square, and here also same, you will get s square. So here you will get what? r2 square is equal to s square into s2 square. Okay, so r2 square is equal to s square into x2 square. From this we can directly write what? r2 is equal to s times of the x2. Okay, so this is the condition, required, this is the condition required to get maximum running torque. Okay, to get maximum running torque. So now what we need to do, just consider this is equation number how much? This is equation number 4. Yes, now assume this is the equation number 4. Now what we need to do, we need to substitute this equation number 4 in equation number 2. Okay, so we need to substitute this equation number 4 in equation number 2, then you will get the maximum starting torque. So that is the reason why substitute equation number 4 in equation number 2. Then what is the equation number 2? So running torque is equal to 3 divided by 2 pi ns into s square into E2 square into R2 divided by R2 square plus s into x2 square. Okay, now what we need to do, instead of this r2 you can directly substitute s into x2. Okay, now you can substitute that value here, you will get the maximum starting torque. Okay, so that is the reason why I'm writing maximum running torque. Okay, so tm means maximum, and here I am writing run, run means maximum running torque, is equal to 3 divided by 2 pi ns into s square into e2 square into r2 means what, s into x2. Okay, s into x2 divided by instead of r2 again I need to substitute what, s into x2 whole square, plus here also same, the remaining term is what, s into x2 whole square. Okay, now by simplifying this you will get what, by simplifying this you will get, so now you have what, now numerator consisting of s square into s, it means s power 3, and denominator consisting of 2 times of s square. Okay, so s square x2 square, so that we can directly write here, so maximum running torque is equal to 3 divided by 2 pi ns into s power 3 into e2 square into s into x2 divided by 2 times of s square x2 square. Okay, 2 times of s square x2 square. Now see here 1 x2 and denominator consisting of 1 x2 cancel, and numerator consisting of s power 3. S power 3 means, sorry, this is s power 3 only, na? Not, this is actually s power 2. I directly written with multiplication of s also. Okay, this is s power 2, and here another s is there, so this s power 2 and denominator consisting of s power 2, by cancelling these you will get 3 divided by 2 pi ns into s into e2 square divided by 2x2. Okay, 2x2, so that from this we are getting 3 into s into e2 square divided by 2 means 4 pi into ns into x2. Okay, so this is the maximum running torque expression. Okay, and the units of torque is Newton meters. Clear? So this is the maximum running torque. Okay, now you can observe most important thing, that is at maximum torque you are getting what, r2 is equal to s into x2. It means that at maximum torque the value of slip is equal to r2 divided by x2. Okay, so this condition is very very important when we are going to draw the slip versus torque characteristics. Okay, so this condition is very very important while we are drawing the slip versus torque characteristics. Okay, so this is about the running torque and also maximum running torque under the running condition of a rotor. Okay, so please do subscribe my channel for more updates.